Hello. Yeah, we have our last speaker of the session. So we have Manoj Joshi, and he's talking about quantum many-body physics with the long ion strings.
Thank you very much. Hello, everyone. First of all, I would like to acknowledge the organizers for giving this kind invitation to talk about some recent work that I've been doing in Institut. So my name is Manoj Joshi. I'm a senior postdoc in the group of Rainer Blatt and Christian Rose at the Institute of Quantum Optics and Quantum Information in Institut. So as you can read the title, I'll be talking about quantum many-body physics with long ion strings. So as Sean already mentioned that, yeah, we always want to have as minimum as noise in the system. We want to have as close system as possible. So I'm not skipping the open many-body physics here, but this is a part of the system because we are in this era of noisy quantum systems. Okay, so the outline of my talk is I'm going to mention about how our quantum simulator system works with trapped ions. I will tell you a bit about how do we engineer the spin-spin interactions, which is the key main work requirement for doing quantum simulation. Then I will just showcase some of the recent results, specifically like spin transport in a long ion string, and how do we basically create spin squeeze state and use or maybe potentially has application in metrological cases. I will also talk about a bit about thermalization in a closed quantum system and large-scale entanglement. So as I said, I will be talking about quantum simulation. When we talk about quantum simulation, it's like, okay, you start with some input state and then you get a final output state while operating some time evolution operator. And in many cases, it is done in two ways. So for example, like one method is basically analog quantum simulation, where you basically implement a Hamiltonian that you are interested into directly in the system and then get the final state as a desired state. The second step is like more a digital approach where you use universal gate sets to basically construct your Hamiltonian that you are interested into, or the construct the unitary time evolution operator that you are interested into. So my work is mainly focused on this analog setting where we use a time evolution operator as it is and construct the Hamiltonian in the lab with certain laser fields or microwave fields, and then apply that Hamiltonian directly on the input state and finally get the final output state. And you measure basically certain observables that you are interested in, such as probability or wave function overlap or certain correlators. Okay, that's one. And now it works. I see. So this is a picture of our lab in Institut. We have a quantum simulator which is related with ions. We work with calcium ion, calcium-40 isotope, which has a nice level structure for doing laser cooling and doing coherent operations. These ions are stored inside a linear Ford trap, which is basically the structure that you see in the middle. It has 4 blade electrodes, which are basically is 1, 2, 2 in the back, and 2 tip electrodes, which are one from left here, one from right. This electrode structure allows us to basically put ions in the middle and trap them for a long time. And we choose our trapping parameters such that it's a linear string. So if you wanted to have other geometries, basically you change confinement parameters such that it becomes a 2D and 3D. But most of my work is basically with 1D ion strings. Typically, these ions are separated by a few micron spacing. For a 51 ion chain, the size is about 250 micron. So to confine the ions, actually, we need some electric field because these are ions. And typically, you can think about that. So suppose you wanted to confine an ion, you use 2 electrodes, put an ion in the middle, which has positive charge, and apply voltages positive and positive on two electrodes. Then it can be trapped in the middle of this electrode structure. That works very well in 1 dimension. As soon as you wanted to trap them into 3 dimensions, you have to basically apply a time-varying electric field. So instead of using a DC field between the 2 electrodes, other 4 electrodes, we apply a time-varying electric field, which basically confines an ion in this pseudo-potential manner. So at the time, the ion is confined in all 3 directions using this time-varying DC electric fields. So once these ions are trapped, we wanted to use some laser field to coherently control them. Specifically for input state preparation, we wanted to prepare them into a product state, which is basically the first step of our quantum simulation experiment. For a calcium ion, simple product state preparation is done onto this electronic level of n is equal to plus half of S half. This we can do when we basically put ions into the trap. We have basically the population between these two ground states. So we basically pump out the population such that we have the population on the right n is equal to plus half state, which is more like a dissipative process. And it allows us to have all ions into spin down state. Just to briefly mention that when I talk about spin down and spin up state, our spin states are encoded into this n is equal to plus half of the ground state and n is equal to plus 5 half of the excited state. This is basically an optical spin, optical qubit or optically manipulated spin states that we can use here. So in our case, basically the transition between plus half and plus 5 half level is at 729 nanometer. So this is simple like a product state where all spins are down. Sometimes we need a product state of where we wanted to specifically choose one spin into a particular direction. That we can do by a tightly focused laser beam, which is shown over one ion at a time. And this can do a resonant X rotation or Y rotation or of resonance, for example, the Z rotations on the block sphere. Typically, in our case, we use a tightly focused laser beam only doing this Z rotation because this allows us to have a reduced crosstalk between the ions. And so, for example, if you wanted to do a particular Z rotation on this ion, you shine it for a particular time, which is defined by the pi time for this this particular ion. And if you wanted to, have other ions into also rotated, you basically shift your laser beam to the desired ion in the ion chain. So typically, we can control at the moment up to 51 qubits in the system. In the future we would like to have more and more ions in this. So we have the possibility of single qubit addressing and global rotations of all the ions into the block sphere. And this actually is also very important key piece of equipment that we need for randomized measurements, which Benma, for example, talked about, that we wanted to have individual ion addressing to rotate individual ion to individual basis. The second important part is when we wanted to implement a Hamiltonian, we need a many-body Hamiltonian, or let's say 2-qubit interaction term in the Hamiltonian. These trapped ions, when we have they have a Coulomb repulsion, but there is no spin-spin interaction, direct spin-spin interaction between them. But what we do, we then engineer the spin-spin interactions by mediating an interaction via the common motional modes, which comes because of we are trapping these ions together. So you can think about that. You have, let's say, two ions which are trapped together. They are repelling each other by a Coulomb force, and there is a trapping force together. So this combined system gives us our coupled harmonic oscillator system. So for two ions, you can have like center of mass mode, we call breathing mode, in phase and out of phase modes. And in 3 dimensions, we can have, let's say, 6 normal modes of motion, and we can use these normal mode of motion to basically engineer the spin interaction. How do we do it? Basically, we use a laser beam which excites the ions electronic state, and while also interplays with the motional degrees of freedom. Because we have these ions which are trapped, the ions motional degree of freedom can be represented by harmonic oscillator, and the electronic degree of freedom, which is spin up or spin down, which is the internal degree of freedom of any individual ion. This harmonic degree of freedom is a common property of all the ions. Spin is it's just the individual ion's spin degree of freedom. When we now use a laser beam to do spectroscopy of these trapped ions, then we see a distinct peak or distinct peaks on the spectrum. First thing, we call it a carrier transition, which excites the ions from spin down state to spin up state while keeping the phonon state the same. Because each of this electronic state has one of these harmonic oscillator, and you excite from one phonon state of the spin down state to one phonon state of the spin up state. So that is basically there is no information about the phonon there. The other peaks that we see in the spectrum are called right sideband, where you you tune your laser beam on the red side of this two-level structure. And then we have some blue sidebands. And these red and blue sidebands are the characteristic peaks of the motion. And why there are so many, they are not different vibrational states, but they are different normal modes, which I was talking about, the center of mass mode, for example, where all the ions move up and down like this. Or we have this tilt mode where the ion string moves up and down in a tilted manner. And in an ion chain, if you use a laser beam which is perpendicular to the ion chain, you see that the center of mass mode has the highest frequency, and the other modes basically decrease in the frequency. And where do we engineer this spin-spin interaction? So if you excite one of these red sidebands, so what you do, you basically go from spin down state to spin up state while changing the phonon state from n to n-1. So when you change the phonon state, all ions know that the phonon state had changed. So that information you can use for making conditional operations on the spin state. Now, also, if you excite the blue sideband, it goes from spin down n to spin up n+1. So to generate the interaction, we use a laser beam which excites its red and blue sidebands simultaneously, not on resonant, but slightly off resonant. And this is something basically we call it a two-photon transition. If you are starting from two ions into spin down state, your blue sideband, for example, excites from one ion from down to up down, virtually exciting the phonon, but the red tone of the laser beam removes that phonon in the system and changes the spin state from down to up. So this is like a resonant two-phonon transition you can think about. This requires both of the laser beams equally away from the sidebands, and allows us to have the Hamiltonian which looks like this. So far I'm only considering one phonon mode, let's call it center of mass mode, but if you have many motional modes, you have coupling strength which depends upon the mode overlap of the motional degree of freedom with the laser beam, which is propagating in a particular direction. And it allows us to have a Hamiltonian, if you consider all the motional modes, approximated by a power law interaction, which has a range which is defined by alpha and strength J0. And these are quite, let's say, controllable in the experiment. So you can change the range of the interaction by basically changing this parameter delta. This tunability actually, theoretically, it is between 0 to 3. On the other hand, practical reasons is always limited between 0.5 to 1.5, depending upon the number of ions that we use. There are, let's say, not only using this easing Hamiltonian, we wanted to also use, for example, a transverse field easing Hamiltonian with certain tricks, and here and there we can generate transverse field easing model or even XY model, which actually the main Hamiltonian that I'll be using for my results later on. So this is actually, as I said, the power law decaying interaction means the interaction strength decreases with the distance. If your particles are next to each other, there is the maximum strength, and then it decreases over the spacing. Now I'm coming to the main quantum simulation results. First project that I will be describing is studying transport properties on a spin chain. What we know from classical hydrodynamics is that your, let's say, diffusion is described by equation of classical hydrodynamics. And most of the time people deal with, for example, like a very short range interaction where normal diffusion takes place. For example, if you take some dye molecule, put it into a beaker of water, these dye molecules slowly dissolve over the water, and this process is basically called normal diffusion. And that strictly works for very short range interaction or maybe dipole-dipole interactions. But what happens if your system is not a short range interacting, but rather a long range interacting system? There, this diffusion happens, and the process of diffusion is described by more algebraically decaying correlation functions. And in our system, because we can tune this range of the interaction, and we can use spin, and can we learn the spin transport and correlate it to the classical hydrodynamics? That was the main goal of this project. The result that I'm showing here is a chain of, yes.
Maybe you said it was destructive. In how many dimensions are you?
Sorry?
In how many dimensions are you?
It's one-dimensional chain. It's a 1D chain. And the first result that I'm showing here is with an infinite temperature thermal state, where we encode some spin excitation in the middle of the ion chain. And the range of the interaction that we set in this case alpha is equal to 1.1. So what we see that with this infinite temperature state, that at time t is equal to 0, what we are measuring here is autocorrelation function. It just tells you how much excitation is remained in the middle of the ion chain. When you turn on the interaction, basically this excitation moves out of the central site, and then you see as a drop of decay of correlations. And this is something very simple. You can think about that you have some excitation and you have some sort of spin excitation changing interaction, then this excitation just moves away. And then there is some sort of a revival, because the way the excitation goes on left and right can come back. It's the same interaction which is moving the excitation, it brings the excitation back. And now, at some point of time, you have a revival. And what happens after that is very interesting, because as soon as the excitation moves for further and further sides, then you have basically a incoherent mixture of many degrees of freedom which play a role in making this transport properties going. So at late time, actually, this decay of correlation is simply like an exponential decay. And this exponential decay is described by basically the Pascal hydrodynamics. So if you have, for example, T to the power minus 1 by 2 or T to the power minus 3 by 2, that decay is described by something like minus 1 over 2 alpha minus 1. Alpha is the range of the interaction. What you see here, we verified these results with different alpha values. Alpha is equal to 1.1, 0.9, and 1.5. And if you want to understand what actually the different range of the interactions do, you can understand it from the phase diagram. So if you have alpha which is greater than 3 by 2, basically you have a normal diffusion, simple to what I showed for dimolecule case. And if you are in between half and 3/2, it's more like a super diffusion. And we see that sort of behavior, not only just by measuring the autocorrelation functions, but also looking at spatiotemporal profiles. First, again, we see for alpha is equal to 0.9. And
sorry, I have a question. So in the previous plot, this pump that you have is the revival.
Yes.
But the time scale at which it happened is somehow close to 1, so which means that the velocity is very large, right? Assuming that the chain is of 20-something size, no? The velocity is very big. No?
Yeah, so this is basically the time scale of J times T. So J times T being 1 is like a perfect hopping of the excitation.
Yeah.
So it's
not a revival. It's just an oscillation. Okay, just an oscillation. Okay.
Yeah, so it's basically
sorry.
Yeah. It's basically just from one side to the other side and coming back. It's an oscillation. It's not going all the way from middle to the edges and then.
Sorry, but what do you say that for alpha larger than 3 by 2 is diffusion? The diffusion should be 1 over square root of T.
Yeah, this is what we see that for if for alpha is equal to greater than 3 by 2, we can describe this one by just
this model is not true for any alpha.
It's not true for any alpha. It is only for example, in this region.
Okay.
So this is what we say that when it is algebraically decaying, for super diffusion cases, this expression is strictly valid. But for alpha 3 by 2, you can just describe this one as T0 minus 1. Which actually happens for people the 3 by 2 you get. Yeah, so we tested this one not only looking at only these autocorrelation function, but spatiotemporal profiles. And one specific example is if you are at the point of alpha is equal to 1 or alpha is equal to 1.5, where the spatiotemporal profiles are described by what's called a Levy distribution function, and specific cases by Lorentzian and Gaussian distribution functions. This is something what we probed, and then we verified that this is working in the system. This required obviously a large system up to 51 qubits. For the tunability that was limited, we only took alpha is equal to 0.9, 1.1, and 1.2. The other project that I would like to describe, I don't know how much time I have.
6 minutes.
6 minutes. Okay, before question time. So let me now change the gear and then talk about a bit more interesting in the sense that how can we characterize a large scale quantum simulator, or most specifically, how can we learn many bodies wave functions which has extensions more than few qubits. Here actually it was very handy to learn that if you have a state of a many-body system which is comprising, let's say, 51 particles, and if that state can be described by some sort of reduced parameter form, let's call it the subsystem A, can be described by some function minus over z, and if this H, what we call entanglement Hamiltonian, has only few parameters to be learned, then the state can be learned very efficiently. Here actually the main assumption comes from the field theory that a reduced state of a full system can be described by some sort of Gibbs state, where this H is, in our case, called entanglement Hamiltonian, is described by some parameter beta I, and Hi are the operator forms. And if you have some idea about what operator forms are there, you have to only learn about betas. And this is, in our case, if you have, say, operator forms which are, let's say, 10 or 20 operators, you have to learn 20 parameters. It turns out that this comes from Bissoniana and Wickman theorem, that if you prepare a state which is an eigenstate of a certain Hamiltonian, this entanglement Hamiltonian contains the same operator form of the Hamiltonian for which you prepare the ground state or the eigenstate. And if you know the operator form now, the task is to learn only these parameters beta. And I mean, just a connection to statistical physics, this beta actually is equivalent to the inverse temperature. More interestingly, it is a local temperature, which we already know that a state of matter can be described by e to the minus e to the minus e over kt, where t is the temperature. So this is what we then tested in our system with a chain of 51 ions. And here we assume that the operator form that we know, because we prepare the state, which is the ground state of a Hamiltonian or a excited state of a Hamiltonian, which we do by variational preparation. So by just measuring the energy of system that you prepare it to a lowest energy state. And then once that state is prepared, you measure certain observables so that you can construct the reduced density matrix with some minimal parameters. Here actually we use classical shadows technique. Thanks, Benoit. He talked about it a little bit. So in that case, we just wanted to learn this beta parameter, measure it into certain observables such that you can learn the parameters, and those are unknown to your experiment. So what you see here, basically, there are two block of plots. The plot on the left, bottom one, is the blue curve is basically the ground state of this Heisenberg model, which I've written as H, which we prepared in the experiment. And what you see here is the parameter beta in the y-axis, and x-axis the size of the subsystem. So the interesting part are basically the site index J or I. What you see here is if you cut your system out of a 51 ion chain, the particles which are in the middle, suppose your subsystem size is, let's say, 12, particles in the middle hardly notice that there is some bath around it, because they are quite far from the boundary or from the cut, which is basically telling you that inverse temperature is very high. The particles find very cold with respect to the bath. And when you move, for example, closer to the boundaries, then you see that the inverse temperature is decreasing, means the particles find more hotter towards the edges. Then we tested this one not only for the ground state, or also for the heated state. And on the right, you see basically not only learning for an isotropic Heisenberg model, but also changing alpha delta, which is 1.7. What is your HI is basically containing all the operator forms that are there. Yeah. So those are only the operator terms. In our case, it's a nearest neighbor Heisenberg model. So what I contains is basically the ion index.
Question. Yeah. But do you have a finite size effect in that? Because it's Bissoniano is. Do you have the same Hamiltonian when it's infinite?
Yeah, so first of all, this was, we don't have an infinite dimension system. It's a finite system. And
I mean, do you see more long runs openings in this Hamiltonian and in this small states?
Yeah, so because this Hamiltonian that we are taking is not the interaction Hamiltonian that we have, but a Hamiltonian for which we prepare the ground state. It's like a measurement phase, the Hamiltonian that we use. So we have the Hamiltonian, which is long range, for which we use as a research, but the Hamiltonian which we are studying is still not long range. We just use our two single qubit and two qubit interaction terms such that the state resembles with the ground state of Hamiltonian. So in that case, there is no long range term present, as long as you can just prepare the ground state very precisely.
It's still the 53 ions?
Yeah, it's a 51 Yeah, 51 but the subsystem that we could probe was up to, I think, 20 particles with this method. So you still needed 20 parameters to be known. Okay, so this is over. Then maybe I don't have much time to talk about the results, but it's basically another very briefly mentioning that this 51 system later on we use for spin squeezing, not only learning the functions with this randomized toolbox, but rather than measuring collective excitation, collective operators, such as spin operator. This was basically at the same time as these results, we had also a nice demonstration in our system where we prepare the spin squeeze states up to 51 particles, and then we push these results further beyond the spin squeeze states. We call it, let's say, two-headed and three-headed cat results. Now I actually won't have time, just coming to the final conclusion side, right? In this presentation, I briefly told you about how a trade-line system works and showed some results, spin squeezing and entanglement studies in our quantum simulation. And to this case, I would like to thank all the organizers and all of you for listening to the talk.
Yes.
There was Jamir.
You can go first.
Oh, it's okay.
Okay, thank you. I wanted to ask you whether you were observing a weird thing occurring at alpha equal 1 or no. Like, because from the point of view of theory, I think that alpha equal 1 is weird because some locality breaks down. So I was wondering if, I don't know, range effects are occurring at the level of transport.
Yeah, so I think there was this mention that this alpha is equal to 1 and 1.5. There are two, let's say, particular points where this there is more analytical form of the Levy distribution function is known. We probably didn't have that much of precision to dig out further whether there is some sort of a non-local behavior can play a role there. But I think certainly we were aware about the fact that these two alpha parameters are more interesting. We didn't reach quite well to alpha is equal to 1, but it was something like 1.1 where we see that the Lorentzian function fits better than the Gaussian function. That was the only two distinct behavior we could observe.
Thank you.
Jamir and then.
So which are the prospects for making the phonons, mediating the spin interactions to be a key player in the game? So right now they mediate instantaneous interactions, but if they end up mediating a retarded interaction, then you don't get more an Hamiltonian spin model as a result, and you can do stuff that other platforms will do differently, study dissipation in the transport while the phonons are active in the dynamic. So is this experimentally doable or?
Yes, so this so far what we just use phonon to mediate the spin interaction, right?
Yeah,
but that is a completely different branch of research. What can be done on this platform is include the phonon degree of freedom, which is like a bosonic system that can be used. There is actually ongoing research going on. For example, Jonathan Holmes' group recently talked about using these phononic modes to do simulation of bosonic systems. So I think there is also a prospect about not only ignoring these phononic degree of freedom, but rather than using it actively for quantum simulation experiment.
Because you start to have technical issues. So it is normally to apply it's like they're fantastic. You change these pockets just testing. So you don't have any technical issue in the experiment?
Well, I didn't quite get while including that technical difficulties. Basically, what happens?
It's my question. Is it a technical?
So I think that difficulty comes when you have many phononic modes. You wanted to map them into the eventually to your measurement basis. And there the difficulty comes that if you have, for example, large phononic state, then you are measuring it always on the spin degree of freedom. So, for example, like the red and blue sidebands I talked about, there, like if you have a large phononic state, you have to take into account that the distribution is as narrow as possible so that you can represent it by a Fock state or a coherent state. Otherwise, the imperfections in the state preparation will show as a measurement error, because eventually you are measuring it into spin degree of freedom, which we call bright or dark state. So there would be some limitation, technical limitation from that side when you go for large and large phononic state. But other than that, I don't see any technical problem immediately.
Yeah, I was interested in the state preparation part. So you say you do BQE. I understand that you somehow do a Fock dynamics with your long-range system and divide it into layers. How many layers? Can you explain a bit more? How many
Yeah, so in this case, the system is still large, but we are playing a trick of using a translationally invariant Hamiltonian. So in the end, it turned out that for a specific input product state, which was a nail state for us, you only need, for example, a global quench Hamiltonian and staggered single qubit Hamiltonian, which is basically light shift on every second ion. And in that case, only 8 layers of single qubit and 2 qubit operations were enough to get the Hamiltonian that we were interested in. But if you wanted to study like more complicated Hamiltonian where there is no translationally invariant part there, then I think it basically explodes with the number of layers that you wanted to use. It gets more and more expensive. In this case, just the 8 layers, 4 plus 4 was enough.
Any more questions? In this experiment that we measured this quantity that gave you the beta ice, you did it in the ground state also?
It was with the ground state and also the excited state. So I think didn't get time to talk about that one. Very briefly. I can go back and show the chart. So the blue one is with the ground state. The ground state of the Heisenberg model. Left one was the isotropic case. The other one is the anisotropic case, just changing the strength of the ZT term. And when we prepare not only the ground state, but more excited state, which was not via the DQE, but first you prepare the ground state and then heat the system to highly excited state via a global quench. Then what we see that the behavior of these, this beta parameter changes, or they become more flat-headed.
For the ground state, as your system gets bigger, these betas should not go through, should not explode. This is what you're showing there. Is that the...
Yeah, so in this case, this is for subsystem size of 12. And beta then also have 11 beta parameters, because only the nearest neighbor terms in the Hamiltonian play a role. And then beta is basically include this h for I is equal to 1 as one parameter, which is small h1. And we just measured 1 beta in our experiment from that. But if you increase the subsystem size, yes, you have to learn more and more betas. And that is still a linear function of your number of particles in the subsystem.
About delta here. So here is for the units with the same preparation.
So delta in our case just tuned. So this is basically the Hamiltonian, which lives in a classical computer, for which you apply certain some gate operations or some 2-qubit and single qubit operations on the quantum simulator, such that you find the lowest energy for the Hamiltonian that you are interested in. So we don't change anything other than just some random parameters in the experiment, such that we can find the lowest energy for this Hamiltonian for which the delta is equal to 1.7. That's more like you treat your experimental parameters until you have the energy which is minimum for a given Hamiltonian, which lives in a classical computer.
A bit confused. So the red one will be for different delta.
The red one is for instead of having the ground state of the Hamiltonian, but excited state. Yeah. But only this one is for different delta is 1.7.
So my point is for the ground state, as you increase the system size, this continue up because in the end it's it equals infinity power that you get, right? Because you're in the ground state.
Yeah. So you mean like the beta should go up?
Yeah. No, it's not the temperature of the system. It's an artificial temperature.
It's a local temperature. Actually, it goes up because of, let's say if you have a subsystem size of 12, and we are looking at an inverse temperature of particle in the middle, which is 6, then this has, let's say, one artificial temperature of beta j. But as soon as you increase the system size to twice, this one finds even colder than before. So it's inverse temperature increases. Yeah, so this will keep shooting up further and further up, which is what we saw. And I don't have that plot now, but we see that it goes up and up when you increase the subsystem size.
So I think there's not enough time for questions. So let's thank.